Today, we're going to dive into something really fascinating, reinforcement learning. You know, it's kind of the secret sauce behind how an AI can teach itself to do pretty much anything. Master a game, have a conversation, you name it. Okay, let's get right into it.
So this question, it really gets to the core of what makes reinforcement learning so incredibly special. I mean, think about it. Instead of being spoon-fed millions and millions of labeled examples, these AI systems, they learn from experience, a lot like we do, right? But how does that actually work under the hood?
You know, this simple analogy is just perfect. It really nails the core concept. Just picture an AI agent, kind of like a digital puppy, and it's just exploring its world. It tries stuff out, and when it does something good, it gets a reward, a treat. This feedback loop, it sounds simple, but is the engine driving some of the most powerful AI we have today.
All right, so let's break down that core idea. It's all built on just a few simple but really powerful building blocks.
The lingo here is actually pretty straightforward. First, you've got the agent. That's our AI, the learner. Then you have the environment, which is just the world it's living in. And this could be anything, right? A video game, a simulation for a robot, whatever. And finally, the most important part, the reward. That's the signal, the little ping that tells the agent, hey, you're on the right track, or nope, bad move.
So these three pieces, they all work together in this constant cycle. The agent looks at its world, it does something, and it gets a reward or maybe a penalty. Then it uses that feedback to tweak its strategy. And this loop just repeats and repeats, sometimes millions or even billions of times. It just slowly gets better and better through pure trial and error.
Okay, but that simple loop has a huge problem. I mean, what happens when the world is just way too complicated to memorize every single possible outcome?
This is where we get a massive breakthrough. The early methods, they basically used giant lookup tables. Think of a huge spreadsheet that stores the value of every possible situation. And that works for simple stuff, but for something like an Atari game, no way, impossible. So the solution was to swap out that table for a neural network. And that created what we now call a deep Q network, or DQN. It basically gave the agent a brain that could generalize from what it's seen and make smart moves in situations it's never, ever encountered before. DQN also had this really clever trick up its sleeve called experience replay. So instead of just learning from its very last action, the agent stores everything it experiences in a kind of memory bank. And then by randomly pulling from this memory, it can learn from all sorts of different past situations. This was absolutely crucial for making the whole learning process stable and way more efficient.
So the AI's got a brain now, a neural network brain. But that created a whole new headache. How do you update that brain without the entire learning process just going haywire and becoming totally unstable?
Well, the answer to that stability puzzle is an algorithm called Proximal Policy Optimization, or PPO. Think of PPO as putting up guardrails. It just stops the AI strategy from changing too much, too fast. And this is so important because it prevents the AI from having one bad update and suddenly forgetting everything it just learned. It makes the whole training process so much more reliable.
And because it was so stable and just worked, PPO quickly became the absolute go-to algorithm. It's the workhorse for pretty much everyone, from training robots to aligning those huge language models that power the chatbots we use all the time.
And that brings us to right now, to the modern era. We've got these incredibly powerful learning models, but how do we teach them really subtle human things, like being helpful or being honest?
This leads us straight into one of the biggest challenges in AI today, the alignment problem. I mean, seriously, how do you teach an AI to be helpful and harmless? You can't just give it a +1 for being nice. The solution, it turns out, needed a totally different way of thinking.
And that new approach is called reinforcement learning from human feedback, or RLHF. It's this really cool 3-step recipe. First, you start by tuning a base model on a bunch of high-quality examples written by people. Then you train a totally separate reward model to be a judge. Humans are shown different AI responses and they rank them, and this judge learns to predict what people will like better. And finally, we bring back our trusty friend PPO to tune the original AI to generate answers that this new judge will score really highly.
And this isn't just some theory in a research paper. The RLHF process is the core technique that's used to train the AI assistants we're all interacting with every single day. You know, things like ChatGPT and Claude, to make them more helpful, less harmful, and just more aligned with what we actually want.
But RLHF, it has a bottleneck, and that bottleneck is us, humans. Collecting all that preference data is slow,
it's expensive. So what's the next step?
Well, the next big frontier is this shift away from subjective human rewards to objective, verifiable ones. So instead of relying on what a person prefers, what if we could just automatically check if an AI's answer is correct? That's the whole idea behind reinforcement learning with verifiable rewards, or RLVR. For things like math or coding, a computer can instantly check the answer. That gives you a reward signal that's fast, scalable, and always consistent.
But there was still this issue of computational cost. You see, PPO often needs a whole separate critic network to work, which can double your memory needs. But a newer method called Group Relative Policy Optimization, or GRPO, has this really elegant solution. Instead of a critic looking at one action by itself, GRPO just has the AI spit out a few different answers and then it compares them to each other to see which one's the best. This relative ranking does the trick without needing that whole extra critic network, which saves a ton of computing power.
And the results from this, they're honestly kind of mind-blowing. When they trained AI models with these objective rewards, they started to just spontaneously develop reasoning skills. Nobody programmed them to do it, but they learned to think through problems, to double-check their own work, and even to use phrases like, wait, let me reconsider, all because doing that gave them a better shot at getting the right answer and earning that reward.
Okay, so let's just do a quick recap of this whole journey. We started with the simple idea of trial, error, and reward. DeepRL gave our agent a brain so it could scale up. PPO made the whole thing stable and reliable, our modern workhorse. Then RLHF taught it to align with human values. And now, these new methods like RLVR and GRPO are pushing us into a totally new frontier, one where AI can learn to reason all by itself, automatically and super efficiently.
So we'll just leave you with this final thought. They say the real test of understanding something is being able to explain it simply. So can you explain why these new methods work so well? If you can put into simple words why GRPO doesn't need a critic, or how RLVR gets an AI to reason, then you've really got a solid handle on how AI is literally learning to teach itself. Thanks so much for joining us.